Okay. Can you hear me? Yeah, put your hand up if the mic is on. Okay, amazing. So we're going to transition the talks, and this is going to be sort of, I guess, part 2 of the day. I know there's going to be some workshops going on in parallel. We've got kind of like a lead up to a panel at the end of the day. So yeah, first up we have Scroll.
Thank you. All right. Well, thanks for the folks hanging out in here. Today, I am talking about an RIP that Scroll's introduced. I was kind of invited last minute. There's a new RIP that we've introduced. If you're unfamiliar with these, we'll talk about them in a bit. But this talk is called RIP 7728 L1sload, Building Towards Interoperability Standards for L2s from L1s. Hearing audio come through. All right, cool. So let's start off with a TLDR. We have L1sload, and this thing is going to enable L2 contracts to read state directly from Ethereum. The gist here is that we're proposing a precompile for the rollup ecosystem that's going to allow contracts on L2s to easily and trustlessly read from L1 storage without all the fuss of complicated proofs and all the cost and complexity that comes with them. Those things are burdensome, and we'll take a look at why. But the agenda here, we did the TLDR. We're going to talk about why L1sload, using L1sload, what it can enable, how it works under the hood, and getting involved if this is interesting to you. I think it's a pretty exciting area of exploration, especially for new devs and hackers, because it starts allowing you to do some of the exciting stuff that all these talks and panels are talking about, but aren't actually accessible yet to devs on the ground building apps. All right, why L1sload? Well, there are plenty of reasons to use L1 state from an L2. There's a ton of value sitting in the storage slots of Ethereum, right? We like Ethereum. It gives us the best security and decentralization guarantees. It is a kind of political common ground, incredibly neutral layer that we can all kind of agree on. It, for a long time, has been the default for protocols, and so there's all sorts of past activity living there. And on top of that, right now, like every rollup has a canonical bridge that finalizes its state there, right? And in that kind of finalized state route, there's a lot of data we can access for those other L2s. So this is enabling cross-chain fun when we get into loading and reading that state. But let's look at an example. So one thing we've been talking about in the kind of chain abstraction space is the idea of this key store. And the idea is, how can users store their public keys, their verification logic for using smart contracts, and authorizing use of assets? Where can we like store this thing so that we can have one copy of it, but it's true across someone's smart accounts on all of their networks? So here we have it kind of like sitting on Ethereum, the L1, right? And to pull in my arbitrary and obligatory diagram from a Vitalik blog post, we have to figure out how are we going to like read this thing across chain and access it, right? And he does a pretty good job here, I think, mapping out what you can do to engage with this data and pull this data. You can do complex things with Merkle branches and ZK snarks. You can use KZG commitments and aggregate those things. But all of those incur lots of cost to users and require lots of infrastructure work on behalf of developers. So in the key store context, Scroll's kind of proposal for how to approach this that we've been working on is really to say, well, why don't we just have all of these L2s read from the key store that is stored on L1, and then L2s can use their capabilities to interact with that L1 to be able to update that. But we know that the key store, the verification logic, all of that sitting on a credibly neutral, censorship-resistant, highly decentralized network. And when you start looking at this, right, like it actually is a little bit more complicated than this, but it makes all these things possible, right? Here's another diagram as an example. I'm not going to walk through the whole thing here, but the idea is that even if that key store contract is not on the L1, because of these L2s are rolling up and posting their current state route back to the L1, if another L2 is able to read that, then you can use a Merkle inclusion proof against the current state of this state route and verify that that is the value. All right, so why a precompile? Why introduce it in this way and get an RIP to get everyone aligned here? Well, it's because every rollup already has the scaffolding for this. We can unlock a huge amount of potential by just leveraging this scaffolding, which exists because of deposits, right? When you deposit your funds from L1 into L2, the L2 has to have a kind of like trust minimized way of understanding how those messages are being passed. So we've introduced this RIP 7728. It's called the L1sload precompile. Check it out if you're interested. I'll give you some more info later on, but let's get into a bit of why we're doing this RIP, why a precompile. Well, one, it gives developers a standard abstraction across all the chains, right? It's going to be a total mess if we have this EVM fragmentation where, on the one hand, Arbitrum does it this way, Optimism does it another, Scroll does it a third. And by giving this kind of like standard abstraction that everyone can use and think about, we also don't have to start thinking about things like how to get your Merkle inclusion proofs for an application or maybe from the client side. Like all of this is just eliminated by saying, hey, tell us the data that you want to grab. We can grab it from you in the context of an L2 smart contract. So by doing this, we're eliminating the kind of Merkle inclusion proofs that we have against the Merkle Patricia trie of the L1 state. Or if we were not using those kind of proofs, we're avoiding all sorts of complicated ZK proving that would be required for wallet implementers and other protocol developers to try and grasp. And really, I think what we're doing is proactively working against a walled garden of ecosystems. And we're seeing this more and more, where there's these ecosystems popping up, and they might all have their own interoperability solution, but we need to be proactively understanding how are we going to pass data in between them and not let these things just be siloed. So what does it look like to use L1sload? Well, we're doing direct reading, right? So we are trustlessly relaying this data from the L1. In the scroll context, we're able to verify this using ZK proofs. And we're making it easy to implement for developers while reducing transaction costs. I think I already kind of addressed all that. But let's see some code. This is more interesting, probably. So this is a function that just loads some information from L1. And this function is a view function where you're going to pass in the contract address and the storage slot kind of keys that you want to load that data from on L1. Here is the precompile address. It's kind of arbitrary right now, but hopefully through the RIP process, the rollup ecosystem can decide on one. But this is the crux of it, right? We have a static call to the precompile address where we pass it a packed set of bytes. That is the address and however many slots we want to read from that. That returns success, and we're able to decode that and return it from the function. So it's really simple. If you think about the context of, say, an ERC20, give the token address and give the slot, which is a little more complicated to assign here when you're talking about mappings, but it's something that developers can easily get into some documentation and figure out and not have to start thinking about implementing in their smart contract code Merkle proofs and anything else. So thinking about what this enables, one example of something that this enables is things like the demo that we did at ETH Berlin with Safe, where you are able to, from an L2, have the exact same signer set and logic for a safe living on L2 as a counterpart on L1. So that way, you have an L1 safe that maybe manages all your treasury and everything else. You update the signers. It's going to be a pain in the ass to go update every single L2 set of signers for that same smart contract, for that safe. However, in this context, you can just set up a guard and say, no, we are going to go read the L1 state of who the signers are supposed to be, and it works out of the box. Other possibilities that this can enable, trustless cross-chain coordination. Like you could think about L1 serving as a way to kind of like lock or unlock things and cross-chain activities. You can think about async composability. You can think about the key store. You can think about other kind of ecosystem agnostic minimal rollups that are able to post updates to L1 and then seamlessly decipher those across different L2s. You can think about bootstrapping new roll-ups with L1 Oracle data, right? It's really going to be, in this world of 10,000 roll-ups, every single one of them having an integration with Chainlink is going to be a mess, right? So we're going to have to find ways to get data to these different chains, and this could be a possibility for that. You could think about like a gaming L2, verifying that you have NFT ownership on L1, where people prefer to maybe hold those NFTs. And we can think about architectures like L2s being co-processors for L1 protocols. So you could offload compute to the L2, still refer to data on the L1, and then post that data back to the L1 through a trustless message passing from the L2 to the L1. All right, so under the hood, what does this look like? So this is going to be kind of specific to Scroll's implementation that we have on our DevNet that's available. But we have an L1 blocks contract. It uses system transactions, and it stores a ring buffer of L1 block hashes and state roots so that any smart contract has access to the last 8,192 blocks from the L2. Now, this is not the last true or finalized or anything else L1 blocks or block hashes. This is the L2's view of that, right? So it's going to be the sequencer's view of what it views as finalized. So in all of these things, if you're thinking about applications for this, and we'll get into this maybe, latency is going to be an issue here, and then also these L2s are going to have to make sure that they have coherent and matching views of the L1. But anyways, we have the following fields for each block. I don't need to necessarily go through these. We have the good block data coming in a contract. And because Scroll's already aggregating all sorts of compute of the EVM via its ZK proofs, we're able to have the sequencer query Merkle inclusion proofs from its L1 node every single time this precompile gets called, right? Precompile gets called, the sequencer itself goes and gets calls what is it? There's an RPC method, I think, called like get storage proof to grab the Merkle inclusion proof. And then it's able to pass that and its information to the prover. And in order to constrain this back on the L1, we have to introduce new values so that every single batch gets constrained to the last L1 block number and last L1 block hash. And we have to make sure that in the contract of L1 blocks, these things match up. And lastly, most of the work is done in these new circuits that we've introduced to verify that these are any kind of valid block number is used and that state roots from the L1 blocks contract are validly executed. Okay, if you are interested in like thinking through the RIP, getting into things, here's some details that I would say that are kind of like interesting to consider. There's still work to be done around figuring out what a standard gas cost across the ecosystem would be. Obviously, we want a premium over just S-load, but we're going to have to figure out how to account for multiple slots. Right now, our proposal is just say there's some sort of fixed gas costs, and then you add the number of slots times a per load gas cost, keeping it fairly simple. Right now, we have a set proposed maximum of 5 slots. This is somewhat arbitrary, so this would be another thing. If you have a use case that would require a lot more, a lot less, you have concerns about that, we would love to hear about it. Latency overall, this whole conference obviously, or mini conference here is a lot about thinking about latency in these contexts. And lastly, we have to think about verification, right? The RIP does not declare how this information is verified. And so we need to consider how burdensome and complex the engineering is going to be for other rollups, whether they're ZK or optimistic. And we would love to hear from other folks in the rollup ecosystem, their thoughts on this. So if any of this interests you, if you want to get involved, please help us iterate on RIP 7728. If you're in a rollup ecosystem, get behind the RIP or don't, but just like get us some feedback. If you're an app dev interested in like testing or doing some ideation, let us know. We'd love to talk about ideas. And if you're a hacker, join us at ETH Global Brussels. We have a DevNet that we're hoping to get people to hack on and play out some ideas with and have some prizes available for that. There's a QR code here that gives you all the information you'd need to like dive deeper into L1sload and to build on our DevNet. And I don't know if I have any time for questions, but if so, let me know. Yes.
So how do you determine at which L1 block number the L2 is supposed to read, right? The state of the slots you're reading may change over time. And I didn't hear you. Presumably the RIP says something about that.
Yeah, so the RIP, the precompile, what it does is going to just read state from the L2's latest view. So like in an earlier iteration of the DevNet and the design we were sending around, you could actually define a block number, but like it was.
So you have to be able to prove which L1 block was the latest L2 view at some point in L2 execution.
Yes, but that's going to just match, I think, also the block that you're utilizing like your deposits for, right? If you're reading incoming deposits and introducing, like basically, we have an L1 transaction type in the network, and what basically the block that gets processed for that is the block, yes.
Let's talk more on that.
Okay, yep, thanks. Also, I did not do the designing and engineering on this, so there's a good chance I'm misunderstanding an implementation detail. Yeah. Yep. So the question is, what happens when the L1 reorgs? So this is, I think, when I say the word latency in there, that is kind of like one of the big aspects, right? So scroll does not process deposits right now, or view L1 as being finalized until 2 epochs, right? And so in the context of a probably more disastrous thing, that is engineering that basically whatever the protocol is going to be doing to itself reorg, it's going to be downstream of that. But right now, like for example, because scroll is like downstream of any, like waits until 2 epochs of finality, like reorgs are not necessarily a thing that we handle or deal with, right? If L1 reorgs, we can, we basically can resubmit commitments to batches. I'm actually coming up against my own limitation of understanding, like, what are the contexts in which after 2 epochs you could even have a reorg outside of like a disastrous fork, right? Because you can, and maybe someone can help me out here, because you have the context of maybe inactivity leaks, but no, that would be, yeah. Yeah, maybe I'm having trouble hearing, and it might just be my own jet lag, but so you're saying that it's...
The latency is 2, that here there will be a required latency of 2 epochs, right? So that you'll at least have Ethereum L1 finalization before you can then do an L1s load. So you'll always have to do an L1s load.
I think the implementation details are actually like, it is a consideration for networks to make, right? But if the networks are able to, I think it's not a requirement to wait until that form of finality, right? Because I know that different networks are working on having like quicker views of L1 state than even waiting for 2 epochs. But like, that's how we're doing it, because that's also how we handle deposits. And I think that's just at the current moment how every other rollup is doing it too.
Another way to ask the question, if you don't wait and the state changes, but you requested it before it changed, how do you handle that situation?
Are you saying the state changes because we have a new view of the L1? Okay. Because yeah, I guess there's 2 contexts in which the state might change, right? One context is just going to be like, I submit my transaction to the L2, and then we've gotten an updated state root from the L1, and maybe that slot's storage has changed on the L1. And in that case, like, there are not protections against that unless you build them outside of the precompile, right? In your smart contract, you could say, hey, this is what I think the current block is. I expect the value to be this. Like, that is all up to the application developer to build those guards around it. The precompile is unopinionated about that. And I think similarly, the RIP as a proposal is unopinionated about how the rollup is. It's not trying to put any constraints on how a rollup is going to handle a reorg. And so in that context as well, the RIP is going to probably be open to like modifications depending on how the rollups approach that. Okay, hopefully that's a tiny bit of clarity, but I'm sure the text of the RIP could probably help me out here as well. So, all right, thanks everyone so much. Appreciate it.